Okay, so now we have a couple of miscellaneous examples, and it says that the focus of a parabolic mirror as shown in figure. So there's a figure over here, and we have a parabolic mirror. So the mirror is something like this, meaning that imagine that you have, for example, something like this. So 1, 2, 3, something like this, and 1, 2, 3, something like this, and then you have these distances over here. And let's suppose that, for example, this goes all the way up to here, and this goes all the way down to here. And let's suppose that I'm doing my best to do this in the best way possible, the neatest way possible. So this is that, and then you have basically something like this. So, and then if I get rid of these things over here, get rid of these over here, I get the parabolic mirror. So this is basically the mirror that we were talking about. That is that, and let's say that this is the concave. So this is your mirror, and this distance over here is 45, and this is the x-axis, this is the y-axis. This is point O, and this is point A, and this is point B. So it says that the focus of a parabolic mirror, so a parabola, as we discussed before, is basically either in this format, or in this format, or basically in this way, or in this way. And we got 4 different equations for these different parabola. And then you have, of course, you have a focus over, you have vertex over here, and you have a focus over here. And this focus over here seems to be 5 centimeters from the vertex. So over here the focus seems to be at 5 centimeters from the vertex. If the mirror is 45 centimeters deep, so the mirror is 45 centimeters deep, and the focus is basically let's call it F, for example, is 5. This point over here, call it F, for example, and it is 5, 0, for example. So the focus is the point 5, 0 on the x-axis. So that means that your C is equal to 5. Okay. If the mirror is 45 centimeters deep, that means that find the distance AB. You want to find this distance AB. Now this seems to be basically let me take a look at these. Let me take a look at these parabolas, and I'll be right. Okay, so now just as a recap. So first of all, what I wrote over here was wrong. This is not the case with a parabola. So just as a recap, basically a parabola is the set of basically this is what a parabola is. So basically you could have something like this over here, and then let's say that you have this. You call the system of parabola. So you have a line over here which is called the directrix. The directrix, and this line is basically, and then over here you have your parabola itself. Of course, this way probably. You have your parabola itself, and then you have some point over here which is called the focus, and this point over here is called the vertex, and this over here is called the axis. This is a parabola. So this is this whole system. You can call it the parabola. Now, through basically all that we did, so we said that this now the equation of a parabola, when we basically derived the equation of a parabola, we put the vertex at the origin. So in order for the equation of the parabola to be in the simplest way possible, we put the vertex at the origin, and the axis of the symmetry we put it, for example, along the x-axis or along the y-axis. Now, if I put this vertex at the origin, I can imagine that I could have, for example, this parabola over here. This vertex is at the origin, and then I have my parabola over here. I have my parabola over here, and then my focus comes over here, and then my directrix basically comes somewhere over here. So then this becomes the, call it line L, which is the directrix. This is the y-axis, and this is the x-axis. And so if in this basic orientation, basically the equation of this line becomes x is equal to, for example, negative a, and the coordinates of this point would be a comma 0. That means that your focus is a units away from the center of the, or from the vertex, you could say, or from the origin, if you put your vertex at the origin. Now that's basically that. Or you could do it the other way around, meaning that you could basically draw your parabola the other way around, meaning that you could do it basically this way, and then your directrix comes over here. Or you could do it basically, for example, this way, in which case the directrix comes over here, and then, or you could do it basically this way, in which case the directrix comes over here, and then this becomes your focus, for example. This becomes your focus. So these are the different ways of representing a parabola. Now, if basically we said that, now this is all as a recap, because there has been some time, there is a time lapse between basically the parabola was, I suppose, the second thing that we discussed in this chapter or in this series of videos, and so even I have really forgotten much. I have forgotten many things about parabola, so I do need this recap. So then basically the four different orientations of a parabola, if you basically put your parabola, if you imagine that this is a coordinate system, and if you put your parabola over here, then your directrix comes over here, and then your focus comes over here, and then the equation, this line becomes x is equal to negative a. The coordinates of this line, of this point, would be a comma 0, and so the equation of this parabola becomes y squared is equal to 4 times ax. If you do it the other way around, meaning that the parabola opens towards the left, then the equation becomes y squared is equal to negative 4ax. So these are these two different orientations of the parabola if the parabola basically opens horizontally towards the right or towards the left. And additionally, you could have your parabola this way. You could have your parabola this way, meaning that if it's, let's say that this is the y-axis and this is the x-axis, and the parabola opens upwards like this, your focus comes over here, your basic directrix is over here, so this is L, and this is basically y is equal to negative a. This point over here is f, which would be basically 0 comma a, and the equation of this parabola in this orientation would be basically x squared is equal to 4 times ay. If it opens in the other way around, meaning that if it opens towards the bottom of the coordinate system, your equation becomes x squared is equal to negative 4 times ay. So these are the four different types of equations that we derived. And the length of the lattice rectum and of course the length of the lattice rectum, which is basically, for example, this line over here, this line segment over here, this is called your lattice rectum, and the length of this lattice rectum was 4 times a. So that's basically almost everything that we said that we talked about parabolas. Now this particular parabola over here, so now we know enough about parabolas. We can now go back and solve our own problem. So now if I come back over here, the question tells me what the question tells me is that the focus of a parabolic mirror is at the distance of 5 centimeters from the vertex. So this is 5 centimeters. And if the mirror is 45 centimeters deep, if it is 45 centimeters deep, find the distance AB. You want to find this distance AB. So of course you know that this is not your lattice rectum, because your lattice rectum would be this line segment over here. Your lattice rectum would be this line segment over here, right? The line going through the focus, basically. So now, in order to find this length AB, you do need to have the coordinates of point A and point B. And to find that out, what you can do, first you need to basically derive the equation of this particular parabola, and then based on that you can of course find basically whatever it is that you want to find. That's basically what we need to do. Okay, so now based on what we discussed before, the equation of such a parabola could be written as basically y squared is equal to 4ax, right? So 4a, so that means that if you know your value of your a, and the focus, we said that it is at the distance of basically a units away from the vertex over here. So that means that this tells me that a is equal to 5. So that means that the equation of this parabola, I can write it as y squared is equal to 4 times 5 times x. So y squared is equal to 20x. That is the equation of this parabola. And of course, this parabola just keeps going in this direction towards the right. But in the first quadrant and in the fourth quadrant. But that's not our concern here. Basically we're talking about this parabolic mirror, and only this section of the parabola is important to us. Now, what we want to do is we want to basically find the length of this line segment AB. Which is now, if you're basically now, I do need to find basically at this point basically my x is equal to 45. So in this equation, if y squared is equal to 20x, if x is equal to 45, then y squared is equal to basically 45 times 20, 20x, 45 times 20, 2 times 45 is equal to 90, so that's 900. Y is equal to 900, that means that y is equal to plus or minus 30. That means that the height over here, is basically if x is equal to 45, over here the height is positive 30, over here the height is negative 30. And so the coordinates of these 2 points would be basically 45, 30, and this point over here would be 45, negative 30. Now, so this is basically from the x-axis. This distance over here would be 30 centimeter, because all the other units are in centimeter, and this distance over here would be 30 centimeter. So the whole distance from here up to here becomes 60 centimeter. 60 centimeter. So that means that then AB is equal to 60 centimeter. That's basically how you would solve this problem. As another example, we have basically a beam is supported at its ends by supports which are 12 meters apart. Since the load is concentrated at its center, there is a deflection of 3 centimeters at the center, and the deflected beam is in the shape of a parabola. How far from the center is the deflection? 1 centimeter. How far from the center is the deflection? 1 centimeter. Okay. So basically what we have over here is a beam that has been, let me read the question again. A beam is supported by its end by supports which are 12 meters apart. 12 meters apart, okay? Since the load is concentrated at its center, there is a deflection of 3 centimeters at the center, and the deflected beam is in the shape of a parabola. How far from the center is the deflection? 1 centimeter. Okay, so you can imagine that basically you have this thing over here, and let's say that this is the x-axis and this is the y-axis, and over here, let me draw these two lines, and I'm going to basically pick these 2 points over here, somewhere over here, and then somewhere over here, and then somewhere over here, and then I'm going to draw a something like this. Okay, so let's suppose that we have this situation, and I want to basically, okay, so let's suppose that this is the beam, and the beam is being supported by these, let's say that there are basically these supports under the beam, and the beam is basically, let's suppose that, for example, this is a log of some sort, for example, under the pressure of some weight, for example, and the beam, the weight has been put over here. The weight has been put over here exactly at the center, and these supports are basically 12 meters apart. This is basically 12 meters apart. And now this log under the pressure of this load has turned into, has basically taken the shape of a parabola. Now, this parabola, if you imagine that this is the x-axis and this is the y-axis, this is the y-axis and this is the x-axis, you have they haven't given me the focus of the parabola. And we have basically and let me just make a screenshot over here. This is not the best drawing that I've ever made in my whole life. So let me do a drawing, a screenshot over here. So now suppose that basically this is the exact situation that that there is in the book, and so if I take this as the x-axis, this point over here, and if I take this as the y-axis, and at this point, which is 3 centimeters, the height of this is 3 centimeters, 3 centimeters, this is basically this length is basically 12 meters apart. 12 meters apart. Now, what you need to know, what I want to know is how far from the center is the deflection 1 centimeter. So if the deflection here is 1 centimeter, here it has to be 2 centimeter. So this has to be a point on the parabola whose height is basically 2 centimeter, and then in order to find that I need the equation of the parabola. But the problem is that the focus of the parabola has not been given to me. Okay, so let me read the solution. Let me see what the solution is. I'll come back with the solution. Well, it turns out that the solution is actually pretty simple. Meaning that basically based on this point, for example, based on this point, you can actually find the equation of the parabola. Meaning that what you can do is that basically this point over here, the coordinates of this point, if you take your coordinate axis, if you take this as x and if you take this as y, then this point over here, the coordinate of this point over here, this becomes basically 6 meters across the x-axis. So that's, if the whole thing is 12 meters, then of course this is going to be 6 meters or 600 centimeters. So that would be 600 centimeters, and the height is 3 centimeters. 600, 3. And so if this is 6 meters, 6 meters would be 600 centimeters, and the height over here is 3 centimeters. Okay, so if the height is 3 centimeters, then that would be the coordinates of this point, and so that means that the parabola actually does go through this point. Okay, so now I have basically taken everything in centimeters, of course, and the equation that I'm going to get is going to work for centimeters. You need to be aware of that fact. So then basically the equation of this parabola can be written as basically x squared is equal to positive 4ay. Now if the parabola goes through the point 600, 3, then I can write 600 squared is equal to 4 times a times basically 3. And so 600 squared, which is 360,000. 360,000 is equal to 12a, and that means that divide by 2 you will get 180,000, and then divide by 2 you will get a 6. 180,000 divided by 2 you get a 3, and that would be basically 90,000, and 90,000 divided by 3 would be 30,000. 30,000, so that would be 30,000. So a is equal to 30,000 then, I suppose, if I'm not wrong. Let me check my answer over here first before going any further. Okay, 60000 divided by 12 is equal to 30,000. Okay. So now if a is equal to 30,000, I can write the equation of this parabola as x squared is equal to 4ay. So 4 times 30,000 is equal to, basically 4 times is equal to 12, 0, 0, 0, 0, y. So that is the equation of the parabola. Now, there is a point over here whose height is basically 2 centimeters. So if y is equal to 2 centimeters, then basically you have x squared is equal to 120,000 times 2, which is equal to 24,000, and so x is equal to plus or minus the square root of 24,000, and that is the same thing as plus or minus the square root of 24 times the square root of basically 10,000, and the square root of 10,000. Okay, so now to get to the answer here, basically what you can do, basically 24 is 2 times 12 and 2 times 6 and 2 times 3. So you can write this as 2 times the square root of 6. 2 times square root of 6, and square root of 110, square root of 10,000 is 100 times 100. So that's 200 square root of 6. That is 200 plus or minus 200 square root of 6. So the answer over here, and this is in centimeters basically. The answer over here, let me see if the answer is right. And if you divide this by 100, you will get plus or minus 2 square root of 6 meters basically, which is the correct answer. Okay. Now that was basically question number 18, and we have another question over here. Let me see. Okay, question number 19 here is a rod AB. So the rod is basically, let me show you the diagram of this rod. So it says that the rod AB of length 15 centimeters rests in between two coordinate axes in such a way that the endpoint A lies on the x-axis and the endpoint B lies on the y-axis. A point x, y, p is taken on the rod in such a way that AP is equal to 6 centimeters. Show that the locus of P is an ellipse. Okay, so now basically about this problem is a little bit basically one thing that you need to know about solving problems, and I'm sure you already know that. Basically, if you don't understand what the problem is asking or what the problem means, you will not be able to solve it. Of course, it's something logical that everybody understands. This problem is a little bit the problem that we have over here is basically a rod AB. This rod AB is basically rests in between two coordinate axes in such a way that AP is equal to 6 centimeters. Such a way that A lies on the x-axis and endpoint B lies on the y-axis, and a point P x, y is taken on the rod in such a way that AP is equal to 6 centimeters. Now you want to show that the locus of P is an ellipse, meaning that P is what the last part actually means is that you want to show that the locus of P is an ellipse, meaning that basically P can be basically traced on an ellipse, whose equation of course we don't have, but of course we can somehow, in relation to other things that we have over here, we can find the equation of such an ellipse. That's basically what this problem means. So what you want to do here, logically of course, then, is that you want to, based on this situation, you want to find the equation of an ellipse that basically on which this point basically P x, y actually lies. That's basically what you want to do. And the solution is pretty straightforward if you understand it, if you know what the solution is. Otherwise, I don't really think that it's really easy to find the solution here. The solution is basically, so you see that this line over here is 15 centimeters, and let me see, since AB is equal to 15 centimeters, so AB over here we know it's equal to 15 centimeters, and AP is equal to 6 centimeters, so this becomes 9 centimeters. Now if you draw these perpendiculars from P to the y-axis and the perpendicular from P to the x-axis, you will have these two triangles PRA and triangles PBQ. And so basically from this triangle PBQ, from triangle PBQ, you have if you want to calculate cos of theta over here is equal to x divided by 9, because it's the adjacent to the hypotenuse. And from triangle basically PRA, from triangle PRA, we have sine of theta. Sine theta is equal to y divided by 6. Y divided by 6. Now you know that from your trigonometry, you know that sine squared theta plus cos squared theta is equal to 1. So you can write x divided by 9 whole squared plus y divided by 6 whole squared is equal to 1. And that means that x squared by 81 plus y squared divided by 36 is equal to 1. And that is an equation of an ellipse. That is an equation of an ellipse. And well, of course, since it does contain x and y, that means that basically x is this, x is the x coordinate of the point P, and y is the y coordinate of the point P. So that means that P is the locus of an ellipse. That's basically all that it is. It's a little bit hard to understand why they have asked this question, but that's basically the answer over here. And as we go forward, then it will make more sense as we use the same logic in a context that makes more sense. Otherwise here you cannot, I cannot really tell why they have asked this question. I don't understand that, but well, it does show that it does show basically how to do a certain things in a certain way, and that is valuable in and of itself. It can be used in many different ways. So that is basically that. So we are done with these examples, and basically in the next video we will talk about some miscellaneous exercises on this chapter, on the whole thing that we did over here. So I will see you in the next video. Thank you.